Hello and welcome to polynomial functions and their degrees. Let's look at a definition of a polynomial function here. We have let n be a whole number and let a sub n minus 1, so forth until we get down to a sub 2, a sub 1, and then a sub 0 be real numbers where one of the a's is not equal to 0. Then the function defined by p of x equals a sub n x sub n plus a sub n minus 1 x sub n minus 1 plus, and go on until we get down to a sub 2 x squared plus a sub 1 x plus a sub 0, we have what's called a polynomial function of degree n. In other words, we look at here the highest exponent, and that gives us the degree. And the number a sub n here, the coefficient of the variable to the highest power, is called the leading coefficient. Now we've actually already looked at some polynomial functions. For instance, when we did just the parent graph y equals x squared, that was actually a polynomial function because notice the power here is a whole number. Remember, whole numbers are 0, 1, 2, 3, 4, so forth. So this is of degree 2 because the highest power is 2. And our understood 1 here is the lead coefficient. So we've already looked a little bit at some polynomial functions. So let's see what we can do with these. We're going to determine if this function is a polynomial function, and if it is, we'll identify the degree. Well, looking at this, I have to make sure that every x has a whole number for its exponent. Well, this has a 7 here, a 5, and that's understood x to the 1, so every x has a whole number for its exponent. And the coefficients are real numbers. Now you might ask about that square root of 3. It may be irrational, but it is real. We can find a place for it on the real number line. So this is a polynomial function, and of course the highest exponent is 7, so that gives it its degree. It's of degree 7, and the lead coefficient is 5 here. All right, let's look at another one. We have h of x equals 9x cubed minus x squared plus 3 divided by x. Think a minute, is this a polynomial function? Why or why not? It's not one because our x is in the denominator. Let's flip back to that definition. And notice that all the x's are in the numerator with whole number powers. So with this x in the denominator, we've got problems. We don't have a polynomial function. In fact, if you will remember, if I brought that x up to the numerator, the sign of its exponent would have to change, and that's not a whole number. It's an integer, but not a whole number. So we can tell this is not a function, a polynomial function. Then we come to this one. Do you notice that x to the 1/4? That's not a whole number, is it? So that is not a function either. Okay, let's move on to the next one. Now you might think with a fraction here that we don't have a polynomial function. But remember, if we're adding fractions, it came or could have come from adding single fractions with a numerator of x squared and a numerator of 4x here. And that would be 1/5 x squared plus 4/5 x. And when we put it in this form, it's pretty easy to see that all our exponents are whole numbers here, and we have real coefficients. So it is a polynomial. The highest exponent is 2, so it's of degree 2, and the lead coefficient is 1/5 here. Okay, let's play around with this just a little bit. The graphs of polynomial functions are smooth and continuous. There are no breaks, no points. So if I draw a function that looks like this, and we wanted to decide if it was a polynomial function or not, our answer would be no, because it has this sharp point here. And polynomial functions don't have the sharp point. All right, let's draw another one and see if this could be a polynomial function. Sure. It's continuous because we don't let up and break anywhere. We've got smooth turns rather than pointy turns. So yes, that is a polynomial function. All right, next time we're going to look at behavior in polynomial functions and see what the behavior at the end of them in particular is like.